my iPad tried to quit. It did not want to participate in the drawing of the acid-catalyzed hydrolysis of the nitrile, but here we are doing it anyways, whether it likes it or not. So we are, anytime we have an acid-catalyzed reaction, I always tell you, if there's an oxygen present, the first thing that happens is you protonate that oxygen. Well, the same is also true with acids and nitrogens. We just don't see nitrogens as often as we see oxygens in our molecules. So this is step one, protonating the nitrogen with our acid. And then once we get that nitrogen protonated, step two, the water molecule, the oxygen on the water molecule is going to come in and it's going to attack the nitrile carbon, and it is going to open up the carbon-nitrogen triple bond. It's going to become a carbon-nitrogen double bond, and we'll have one lone pair of electrons on the nitrogen. We do have a positive formal charge on the oxygen, so another water molecule is going to come along and deprotonate. And we have this intermediate right here. I have no idea what I am doing to make it continue to do that. I must be touching something. Okay, so where are we at? We just protonated our water molecule, so we made an H3O plus. And that H3O plus wants to protonate our intermediate. It would love to protonate the oxygen, and it probably does, but that just takes us back to the previous step, and we're trying to move forward. So instead of protonating the oxygen, we're going to protonate the nitrogen. And that gives us an NH2. Still have the double bond between the carbon and the nitrogen, so now we have a positive formal charge on the nitrogen. We can draw a resonant structure for this molecule. In our resonant structure, we're going to take one of the lone pairs of electrons on the oxygen, move that down to make a carbon-oxygen double bond, and move out the carbon-nitrogen double bond. So now our positive charge is on the oxygen instead of on the nitrogen. And with the water molecule from up here, we can deprotonate. We're going to deprotonate with the oxygen of the water molecule, pull the hydrogen off so that we can get rid of the positive formal charge. Isn't this so relaxing? And here again we have made ourselves an amide. We also made an H3O plus. So now we have an acid in the presence of oxygen. We're going to protonate the oxygen. If you're asking yourselves, why not protonate the nitrogen? Sure. We're trying to move ourselves forward in this reaction. So once we get that amide protonated, the water molecule that we just made can attack the carbonyl carbon, open up the carbon-oxygen double bond. We've got a water molecule down here with a positive formal charge and an NH2. A lot of stuff going on there. We are going to, the next thing that we're going to do is let's deprotonate again with that positive charge. This is such a beautiful mechanism, such a soothing mechanism. And we made an H3O plus in that last step. So let's go ahead and protonate. Let's protonate something new. Now it's nitrogen's turn to get protonated. And what we have done for nitrogen now is turned it into a good leaving group. We've turned it into what will be an NH3, which is a great leaving group. That's the ammonia molecule, so it's very stable. Let's bring a lone pair of electrons down from either one of the oxygens and spit out that NH3 molecule. It's a good leaving group. We've got a positive charge on our oxygen now. And an OH. And we have made this NH3 molecule, ammonia, which is a decent base, and we can go ahead and use that lone pair of electrons on ammonia's nitrogen to do the very last deprotonation that we need to give us the carboxylic acid. The end. What a lovely mechanism.